Thank you all very much for joining us. Super excited to have all you here, and super excited for Emma Dodderman to join for a lecture. I've known Emma for at least 5 years and always been super fan of your research, and so again, very, very glad to have you talk with us today. Emma Dodderman is a PhD candidate at UC Berkeley, where her research interests include computer security systems and applied cryptography. Received the Microsoft Research Ada Lovelace Fellowship, the NSF Graduate Research Fellowship, and the UC Berkeley EECS Excellence Award. So with that, thank you for joining us.
Yeah, thank you so much. It's great to be here with all of you. OK, so today, web servers store massive amounts of sensitive information. So for example, they store tax returns, emails, health data, photos, messages, location data, and search queries. And all of this information creates a target for attackers. So for example, when I was a PhD student at UC Berkeley, attackers broke into databases storing student and staff social security numbers. They broke into this database, posted the contents online, and unfortunately, these types of data breaches have become relatively commonplace. And so the way that we've addressed this by building systems is by adding components in order to protect data. So for example, we rely on single sign-on servers in order to manage user credentials. We rely on client-side hardware security keys like YubiKeys or passkeys in order to protect user cryptographic keys from potentially compromised laptops. And we rely on hardware security modules in order to protect secrets from potentially compromised web servers. And all of these components make it harder for attackers to steal data. But all of these components are also vulnerable to compromise. So for example, back in 2018, attackers exploited a vulnerability at Facebook in order to steal roughly 50 million Facebook access tokens, which allowed them to access accounts that were linked via sign-in with Facebook. There have also been vulnerabilities in client-side secure hardware devices. So there was a bug in how these Infineon Trusted Platform modules were generating RSA keys. And so users who had used these devices to generate their RSA keys were actually worse off than if they had just generated them on a commodity laptop. And even hardware security modules are also vulnerable to compromise. So researchers have shown how to exploit bugs in the firmware or physical access to the device in order to extract secrets. So all of these components are vulnerable to compromise. We can't trust any of these in order to protect our secrets. And so this has led us to this world where data breaches are widespread and damaging. So in 2023 alone, there were over 3,000 data breaches affecting roughly 350 million individuals. And the human cost of these data breaches is quite high. So for example, in 2021, attackers broke into the databases of a Finnish mental health clinic. They extorted patients and posted patient social security numbers and therapy records online. And at the end of 2023, attackers exploited a vulnerability in order to steal large amounts of genetic data from 23andMe. They targeted individuals of Ashkenazi Jewish and Chinese descent and posted this information online, leading to fears around how this could be used for potential genetic discrimination. So all of these components are insecure, and this has led us to this world where data breaches happen all the time, and they have a high human cost. So how do we move forward from here? If we can't trust any of these components, how can we hope to protect user data? And so the way that I've addressed this in building systems is by building systems that provide strong security and privacy properties, even if the individual components are themselves insecure. So I've thought about how to have the benefits of single sign-on, even if the single sign-on server is compromised and large. How to have the benefits of a hardware security key, even if the key is buggy or backdoored in True2F. And how to build an encrypted backup system that relies on secure hardware without having to completely trust the secure hardware device and our system safety pin, and then some subsequent follow-up work with the Signal end-to-end encrypted messaging application. And I've also thought about how to protect user queries from potentially compromised web servers in Tiptoe, Dory, Snoopy, and Waldo, and how to protect user queries on the network in Lightweb. And in all of these systems, I think about how we can define new models that fit real-world needs, and then from there, how we can tailor cryptographic tools to our particular system setting. So in particular, how we can provide the minimal necessary cryptographic tools in order to reduce overheads. And in this talk, I'll focus primarily on Larch, and then I'll touch a bit on our system safety pin for encrypted backups, and how the security guarantees in safety pin have inspired some ongoing work with the Signal end-to-end encrypted messaging application. OK, so I'll start off by talking about Larch. So today, not only do data breaches happen all the time, but when they do, we're actually really bad at identifying them. So in 2023, it took organizations on average 204 days to identify a data breach. And over half of these data breaches are due to human elements like credential theft and phishing attacks. So if we were better at detecting when these things happen, we could then be better at detecting data breaches and then take steps in order to mitigate the effects. So if we can't prevent compromise, the next best thing to do is to be able to detect it quickly. So ideally, we'd like to be able to record all the logins that take place in the system. So imagine we have some logging server, and this logging server is going to record all the authentications made by some user. So I authenticate to GitHub and Slack, and this is recorded. And even if an attacker breaks into my laptop or steals some user secrets, any authentications that they make to my accounts should also be recorded. So if the attacker authenticates to my Wells Fargo account, the log server should have some record of this authentication. And this is useful because now a user can go and request the contents of the log, examine this, see which authentications it doesn't remember making, and then take steps in order to mitigate the impact. So one way to get closer to this goal is using a system like single sign-on. So we can think of single sign-on as being sign in with Google or some sign in through the university or an organization like Okta, for example. And this is convenient because the user only has to remember one password. But one advantage of single sign-on that you might not think about is that the single sign-on server can also keep a log of all the authentications taking place. And intuitively, this makes sense because the single sign-on server is on the critical path for every authentication in the system. So every authentication is routed through the single sign-on server, and so it has a comprehensive view of everything that's happening. And in fact, Okta allows an admin to go in and see all the authentications made within an individual organization. And this is useful for auditing when something goes wrong. But when we get this nice new auditing functionality, we're also creating new problems. So in particular, the single sign-on server becomes a single point of security failure in the system. So because the server is storing user credentials, now if an attacker breaks into the single sign-on server, it can access potentially many users' accounts. And we saw this happen at the end of 2023 when attackers broke into Okta's customer support unit and stole authentication tokens, which allowed them to break into accounts that were linked via Okta. So Cloudflare discovered that they'd been breached just last month using authentication tokens that were stolen from Okta. And the single sign-on server also becomes a single point of privacy failure. So the server is storing large amounts of customer information, so user names, emails, where users have accounts, how often they're authenticating, and all of this information creates a target for attackers. So we saw at the end of 2023, attackers broke into Okta's servers and stole large amounts of customer information. And so the single sign-on server is truly a single point of privacy failure as well. So if we come back to our earlier goal, we'd like to be able to record all the authentications in the system, but we'd like to do so with strong security and privacy. So we shouldn't have to trust this logging server with user credentials or other private user information. And one challenge in achieving this goal is that existing authentication protocols are hard to update. So applications are already running authentication protocols, some based on passwords, authentication codes, security keys. Many of these are standardized, and it can be challenging to convince these applications to update to new authentication protocols. So to achieve this goal while addressing this challenge, we built Larch, which provides the benefits of single sign-on without creating a single point of security or privacy failure. So we can have this enforced logging, but without having to trust this log server with client credentials or private client information. And we can do so in a way that's backwards compatible with existing web servers. So Larch works with existing web servers in an unmodified way. They don't even need to be aware that this new Larch log server even exists. I'm going to walk through these properties in a bit more detail. So we want this log enforcement property where we ensure that every authentication, whether it's made by an honest user or an attacker that's stolen user secrets or broken into the user's device, is correctly logged at the log server. So more precisely, the client is going to have some secret encryption key. I'm going to write this as SKEnc. And after every authentication, the log server gets access to some ciphertext encrypted under the client's encryption key of the web server's name. And we also want to provide strong security. So this log server shouldn't become a single point of security failure in the system. And this means that it shouldn't be storing any credentials so that if an attacker breaks into this server, it can't access any user accounts. And we also want to provide strong privacy. So this log server shouldn't be learning any information about where the user is authenticating beyond timing. So more precisely, after every authentication, the log server is just going to learn some ciphertext encrypted under the user's encryption key. And because the log server doesn't have the corresponding decryption key, it doesn't learn any information in a cryptographic sense about which web server the client is authenticating to. And finally, we don't want to require any changes to the web server. So everything should look the same from the web server's point of view. It shouldn't even need to know that this new large log server even exists. So the challenge in designing Larch is this tension between log enforcement and client privacy. So on the one hand, for log enforcement, the log server must correctly record the web server's identity. So whether it's an honest user or an attacker that's stolen user secrets or broken into the user's device. And this is precisely the property achieved by existing industrial single sign-on systems. On the other hand, for privacy, we want to ensure that the log server doesn't learn the web server's identity. And there's been some prior academic work on single sign-on systems that provide strong privacy properties for users. But no one's really looked at how we can get this log enforcement property with strong privacy. So this is essentially the problem of correctly recording without actually seeing where the user is authenticating. So how can we get both of these at the same time? And to make it clear why this is hard, I want to show you why a simple solution doesn't work. So let's imagine that we have some client, and it's just going to run any existing authentication protocol with some web server. So this could be based on passwords or authentication codes. And then after the client authenticates, it's going to send a ciphertext to the log server. So just an encryption of the web server's name. The problem with this approach is that an attacker can lie without detection. So there's nothing stopping an attacker from sending a ciphertext of the wrong web server's name to the log server. So for example, sending a ciphertext encrypting Netflix when the attacker's actually authenticating to GitHub. And the log server has no way of knowing that it's actually receiving a ciphertext that isn't correctly bound to the web server's name. Furthermore, the attacker could even choose to not send any ciphertext at all, and the log server would have no way of knowing that an authentication is actually taking place in the system. So while the solution provides the security and privacy we want in a backwards compatible way, it doesn't actually provide the log enforcement properties that we care about. So the key idea for overcoming this tension is to split control between the client and the log server. So when we authenticate today, the client has some secret. I'll write this as SKLogin. This could be a password or a cryptographic key, and we use this secret to run some authentication protocol with a web server. The key idea in Larch is that now we're going to split this secret between the client and the log server. So the client has one half, the log server has the other half, and now they're forced to interact through some new protocol every time there's an authentication. And this new protocol can provide the properties we wanted, so log enforcement with strong security and privacy in a backwards compatible way. And intuitively, it makes sense why we get at least some of these properties. So the client only has one half of this secret, and so it's forced to interact with the log server for every authentication. And because the log server only has one half of the secret, it can't become a single point of security failure in the system. So by running this interaction, the client gets something that it can use to authenticate, and the log server is going to get a valid encrypted log record. And to construct this protocol, we're going to use two powerful cryptographic ingredients. And I'll talk about these at a high level and then show how we instantiate them in our protocol. So we're going to use two-party computation, which allows two parties to jointly run some computation and only learn the outputs. So any inputs and intermediate values remain hidden. And we're also going to use zero-knowledge proofs. So these allow us to prove that some statement is true without revealing any evidence for why this is the case. And both of these can allow us to achieve the properties that we want in theory, but the challenge is instantiating these efficiently in practice. So how can we tailor these tools to a particular system setting in order to reduce the overheads? So Larch needs to support existing authentication protocols. So we designed, implemented, and evaluated Larch protocols for password-based login, authentication codes like those generated by apps like Google Authenticator or Authy, these 6-digit codes that are valid for 30 seconds or a minute, as well as a signature-based protocol. And traditionally in these protocols, a cryptographic key is stored on some hardware security key, but it can also be stored on a user's laptop or mobile device. And in this talk, I'll focus primarily on Larch for a signature-based protocol, but you can also see the paper for details on the other protocols if you're curious. OK, so now I'm going to dive into some more technical material. So as a starting point, let's just take a signature-based protocol as it exists and is standardized on the web today. So in these protocols, the client has some secret signing key, and the web server has some corresponding public verification key. And to authenticate, the web server is going to send some random value to the client. The client is then going to use its secret signing key to sign some hash of the web server's name along with this random value. And then it sends the signature back to the web server. And the web server can then verify using its corresponding public key. So this is just a simple challenge response-based protocol. So now to split control and Larch, we're going to give one half of the signing key to the client and the other half to the log server. And we'll also give the client a corresponding encryption key. Now, to achieve the properties that we want, we could use some generic two-party computation framework, which can allow us to run any generic computation inside of some two-party computation protocol. And so the client could input its information, the log server could input its half of the secret key, and the log server would get a ciphertext, and the client would get a corresponding signature. And this would allow us to achieve the properties that we want. But the challenge is that it would have a relatively high cost, because now we need to do all of these computations in a generic way, and we can't exploit the structure of this particular computation. And so I'll show you how we can minimize the use of cryptography so that the overhead is roughly 2 orders of magnitude cheaper. So instead, we're going to break this into cheaper steps. So I'll talk about these steps at a high level. So in the first step, the client is going to send the log server some ciphertext, so an encryption of the web server's name under the client's encryption key. And then in the second phase, the two parties are going to use their halves of the secret key in order to jointly sign this message. So the hash of the random value along with the web server's name, and the client can then use the signature in order to authenticate to the web server. So this is the high-level overview, but we're still missing a few key steps. So the first problem that we face is that, as I presented it, the client can still send any arbitrary ciphertext to the log server. So we have no way of enforcing that the ciphertext is actually correctly bound to the web server that we're authenticating to. And so I'll show how we can use a zero-knowledge proof with tailored constraints in order to solve this problem and bind the ciphertext to the web server that the client authenticates to. The second challenge is how do we do the signing in a concretely efficient way when the signing key is split between two parties? And here I'll show how we can use two-party computation adapted particularly to our system model in order to do this efficiently. OK, so I'm going to start off with the first challenge. So how can we bind the ciphertext that the client sends to the web server's identity? So what we need a zero-knowledge proof tying the ciphertext to the message that the client and log server will jointly sign. And this zero-knowledge proof needs to certify two things. So the first is that the message that they're signing and the ciphertext are actually for the same web server. The second thing is that an honest user can later correctly decrypt the contents of the ciphertext. So this means that the ciphertext should actually be encrypted under the honest user's key so that it can actually be later decrypted by an honest user. So we can certify this by having the zero-knowledge proof guarantee that for some hidden ID, and here we can think of ID as just being the string GitHub, the ciphertext is an encryption of that ID, and the message is a hash of ID along with some random value. So here we get the first property because these are committing to the same ID. And for the second property, we can ensure that an honest user can correctly decrypt the contents of the ciphertext by giving the log server a public key corresponding to the client's secret encryption key. And now the log server can use this public key in order to check that the ciphertext was generated under the correct key, even though the log server can't actually decrypt the contents of the ciphertext. So the public key makes it possible to verify without actually decrypting the ciphertext. And this approach provides the properties that we want. But now we need to prove something about a public key encryption scheme inside of the zero-knowledge proof. And so this is going to incur higher overheads. And so we show how we can actually reduce costs by using only symmetric key operations. So we can actually reduce the cost by, instead of giving the log server a public encryption key, we're going to instead give it a commitment to a secret symmetric encryption key. And so now we can only use symmetric key operations inside of the zero-knowledge proof. But we need to check one additional constraint. And this is that the commitment that the log server has correctly matches the encryption key that the client used to generate the ciphertext. So by adding this one additional check, we can now use symmetric key operations, which are orders of magnitude cheaper. OK, so now I've talked to you about how we can deal with this problem, where the client can send any arbitrary ciphertext to the log server by using a zero-knowledge proof with tailored constraints. And so I want to transition to talking about how we can do the signing in a way that's concretely efficient when the secret key is split between two parties. So for backwards compatibility reasons, we're tied to particular signature schemes. One of the schemes that these web servers are required to support is ECDSA. And there's been substantial prior work on doing threshold signing in ECDSA, so when the key is split between two parties. But this work has relatively high communication and computation costs because it's in a slightly different setting than ours. And so we thought about if we could take advantage of the particular system setting that we're in order to reduce the associated costs. So we returned to two-party computation as it exists in a generic setting. And many two-party computation protocols operate in this idealized model with a trusted dealer. So imagine we have some trusted dealer that's going to generate some correlated randomness. And this trusted dealer is then going to distribute shares of this correlated randomness between the client and the log server. So here are the two parties in the computation. And then these two parties can use these shares of the correlated randomness in order to run the computation more cheaply. The challenge is that in the real world, we don't have this trusted dealer that we can trust in order to securely and privately generate our correlated randomness. And so instead, we've developed these protocols in order to do this in a secure two-party way. And these protocols have improved substantially over the years, but they're still much more expensive than actually using this correlated randomness in order to execute the computation. And so our insight in Larch is that in our setting, we actually do have this trusted dealer entity. And this is precisely the client when it first creates an account with the Larch log server. So when the client first creates an account, it needs to be honest. Otherwise, we won't get any security guarantees moving forward. And so when the client first creates an account, it can generate a bunch of correlated randomness and distribute half of it to the log server. So now the client has a large amount of correlated randomness, and the log server has the other piece of this. And for each authentication, they can use a piece of this correlated randomness in order to do the signing process more quickly and efficiently. Each piece of correlated randomness can only be used once, and so you might worry that eventually the client and log server will run out of this correlated randomness. But we actually show how you can securely and privately refresh this by taking advantage of the particular system setting that we're in. And the details are in the paper, and I'm happy to talk about it later if people are curious. OK, so zooming out, I've now talked about how we can do the signing in a way that's concretely efficient when the signing key is split between two parties. OK, so I promised that we would achieve these 4 properties earlier, and I want to talk about how the protocol that I presented actually achieves these properties. So the first property that we wanted was log enforcement. And here we get this because the log server is only going to participate in signing once it receives a ciphertext along with a valid zero-knowledge proof. So once it's convinced that it's received a valid encrypted log record. The second property we wanted was strong security. And here we get this because the log server only has 1/2 of the signing key. And so even if an attacker breaks into the log server, they can't sign challenges to authenticate to the user's account. We also wanted privacy. And here we get this because the client is sending a ciphertext to the log server along with a zero-knowledge proof. And from this, the log server learns no information about where the client is authenticating. And finally, we didn't want any changes to the web server. And here we get this because the client, or the web server is still sending some random value and then getting back a signature. So it doesn't even need to know that the signing is now taking place between the client and the log server. OK, so how does this actually perform? So we measured the overheads. As expected, the overheads at the web server and between the client and the web server are unchanged because the protocol is exactly the same. But the interesting pieces are the overheads between the client and the log server and the overheads of actually maintaining a log server. So we measured the latency and communication costs of this interaction, as well as the throughput at the log server and the per-user storage costs. And you can actually offload the per-user storage costs for future authentications to the client if this is burdensome for the log server. And most of the overheads of this interaction between the client and the log server are due to the zero-knowledge proof. But the nice thing here is that as these zero-knowledge proof systems get better, and they've improved even since the time we published this paper, the cost of this interaction will also be reduced as well. And to put these numbers in perspective, as a baseline, we could consider the cost of generating a signature on a hardware security key. So if we don't split the cryptographic key between two parties, it's common practice to store it on some secure hardware device. And the cost of generating a signature on one of Google's hardware security keys is 23 milliseconds, not including the time it takes for the user to actually tap the button to initiate the signature. OK, so now I've talked about Larch for a signature-based protocol. But we also designed, implemented, and evaluated protocols for authentication codes, as well as password-based login. OK, so zooming out even further, I've talked about how we can develop this model in Larch for having the benefits of single sign-on without the corresponding drawbacks in a way that's backwards compatible. And to do this, we can provide the minimal necessary cryptographic tools, so tailoring zero-knowledge proofs to our setting, and then also using two-party computation adapted to our system model. And so now I want to transition to talking about SafetyPin, which is a system for encrypted backups that relies on secure hardware without having to completely trust it, and then talk about how the security guarantees in SafetyPin have inspired some work with the Signal end-to-end encrypted messaging application. So user devices today store secrets. So for example, they store the secrets in large, so half of the signing key along with the encryption key. But they also store all kinds of other sensitive information, like our financial documents, photos, messages, and contacts. And all of this information should remain hidden from servers. But users are also not very good at taking care of their devices. We break our devices, we lose them, they're stolen. And when this happens, users still want to have access to their data. So one way that we could allow users to still have access to their data is by backing up their data and encrypting it using something that users can remember. So users, unfortunately, can't remember 128-bit cryptographic keys. But users are good at remembering, for example, short pins, like the 6-digit pins that you use to access your iPhone or Android phone every day. And so you could imagine encrypting this backup data using a short pin that the user can remember, and then sending the ciphertext to some backup provider that can store it for when you later want to recover your data. The problem with this approach is that if a backup provider is compromised, it can just try all possible pins in order to recover the user's data. So these pins don't provide very much entropy, and so if the attacker wants to recover your data, it can easily try just all possible values in order to recover the user's secrets. So this doesn't provide a good defense against pin guessing attacks. And so the way that industry has addressed this is by using secure hardware. So Apple, Google, WhatsApp, and Signal have proposed and deployed solutions based on secure hardware. And the high-level idea is that the hardware is only going to permit a small number of pin guesses. So now if an attacker can subvert the backup provider but can't subvert the secure hardware device, it can only get a small number of pin attempts. And this approach essentially strengthens this low-entropy pin that a user can remember. And so now the attacker can't actually get that many guesses to recover the user's data. The problem with this approach now is that the secure hardware device becomes a single point of security failure in the system. So while these secure hardware devices provide a strong defense against attacks, they're not immune to compromise. An attacker that wants to break into one of these devices, particularly one that has physical access, could launch some side channel attack or use some advanced imaging techniques in order to extract secrets from the device. And so an attacker that's determined can break just one of these devices and steal potentially millions of users' backups. And so the system doesn't provide a strong protection against physical attacks. And so in SafetyPin, we thought about how we can have the benefits of secure hardware devices without having to completely trust them. And so we split trust across many of these devices in order to provide a strong protection against physical attacks. And so now an adaptive attacker has to break into many of these devices before it can recover any user's data. And so this provides a strong protection against an attacker that wants to break into these devices to recover user backups. And the challenge in designing SafetyPin is this tension between security and scalability. So for security, we want to ensure that an attacker needs to break many devices before it can recover any user's data. And this would suggest a solution based on secret sharing the data across many of these devices. On the other hand, for scalability, the client should only have to contact a relatively small number of devices in order to recover its data. And we want this property so that we can add more devices to the system in order to handle more requests. But now there's fundamentally this mismatch between the number of devices that an attacker needs to break in order to recover any data, which should be large, and the number of devices that a client needs to contact before it can recover its own backup, which should be small. So the way that we overcome this tension is by using the user's PIN in order to identify a small hidden group of devices. So this PIN doesn't provide much entropy, but it provides just enough to hide the set of devices that an attacker would need to break into in order to recover the user's data. So now an attacker would need to break into additional devices in order to get additional PIN attempts. And this provides a strong protection against these physical attacks. And I want to show how this works in a little bit more detail. So we devised this location hiding encryption scheme. So now to back up data, the client is going to start off by sampling some user-specific hash function. And it will evaluate this hash function on the user's PIN in order to get the set of devices that the user will back up to. Now it will break the data into many secret shares. So each of these secret shares will individually look random, but together they'll allow the client to later reconstruct its data. And then the client will encrypt each of these shares to each of the set of devices that its PIN hashed to. And it will send the hash function along with the ciphertext to the backup provider. And I just want to note here that we're using a user-specific hash function in order to ensure that the same PIN doesn't map to the same set of devices for every user. So a common PIN like 1, 2, 3, 4, 5, 6 doesn't always map to the same set of devices. So now in order to recover, the client is going to fetch its hash function along with the ciphertext from the backup provider. The client will evaluate the hash function on its PIN in order to get the set of devices. And then it will send the ciphertext to these set of devices that can decrypt. The devices will decrypt and then send back the shares of the data, which the client can use to reconstruct the contents of its backup. And there are a few features of this design that I want to highlight. The first is that we need to use an encryption scheme that hides the location of the devices that we're encrypting to. So it's important that if the backup provider just has a bunch of ciphertexts, it doesn't know which set of devices the client will contact in order to recover. And so we need a key private encryption scheme. Also, finding the right devices implicitly proves knowledge of the PIN. So if the client knows which devices to contact, this is enough to prove that it actually knows the right PIN, and so the client doesn't need to actually send any information about the PIN to the devices. It's enough that it just found the right set of devices. And finally, we want to allow the user to recover their data, even if some of these devices fail in a benign way. And so we can actually share this data in a way that has some redundancy, so using threshold secret sharing in order to allow the client to recover its data, even if some of these devices fail. And while this location hiding encryption scheme solves a lot of the problems that we care about, it also introduces some additional challenges. The first challenge is that an attacker can see which devices to break into after recovery. So when the client recovers, it's going to send its ciphertext to several of these devices. And an attacker that's watching the network can see which devices the client is contacting in order to see which devices it would need to break into in order to recover the user's backup. So essentially, by recovering, the user is now sacrificing its privacy. And so the way that we deal with this problem is by allowing the devices to revoke their ability to decrypt just one user's backup. So now if an attacker tries to break into these devices after they've recovered for a particular user, this device is no longer going to be useful for recovering that particular user's backup, and this provides a strong defense against an adaptive attacker. And so there's some cryptographic primitives that can allow us to achieve this. So puncturable encryption is a cryptographic primitive that allows you to revoke the ability to decrypt. But this primitive is relatively heavyweight, and so we show how to modify it and adapt it to a setting where you have limited computation and storage constraints. The second challenge that this introduces is how we can securely and scalably track recovery attempts across all devices. So the reason that we added secure hardware devices in the first place was to provide some rate-limiting mechanism for how many attempts that you get at the PIN before you can recover. But now if different PINs are mapping to different devices, it's not enough for one of these devices to just keep some local counter of the number of attempts that a user gets to recover. So we'd like the security of every device having a counter for every user. But at the same time, for scalability reasons, we don't want this. Each device should have to do a relatively small amount of work. And so we build a distributed append-only log where each device has to do a small amount of work, but with high probability, any misbehavior will be caught. So not only does SafetyPin provide the security and scalability properties that we want in theory, but I actually implemented this in practice and showed that this works well with existing resource-constrained embedded devices. So I built a prototype with 100 low-cost secure hardware devices, so 100 $20 solo keys, and showed that the cryptographic primitives that we used actually work well on these devices that have limited compute, communication, and storage. And the security guarantees in SafetyPin have actually inspired some ongoing work with the Signal end-to-end encrypted messaging application. So Signal has a similar problem where user devices are storing chat histories and user contacts, and all of this information should remain private from the Signal servers. But at the same time, users want to be able to access this data even if they lose their device or it's broken or stolen in some way. And so Signal's prior solution required trusting Intel SGX, so a secure enclave. And this approach provided a strong defense against a compromised backup provider. But now if an attacker can exploit some vulnerability in SGX, they can then recover many users' backups. And so we help them design a solution that splits trust across different types of cloud secure enclaves, so that now an attacker would need to compromise all three of them simultaneously in order to recover any user's data. And the challenge here was building a system that scaled to tens of millions of users and was operational at that scale as well. And deployment is in progress, and the code is online. Yeah?
I can totally understand the last deployment story. So my question actually has to do with like your original picture. Suppose all I wanted to do was to compromise not a targeted user, but some user or some set of users. Presumably, I could just compromise some of the keys, and that would potentially give me some users I couldn't necessarily target directly, but it would allow me to reverse engineer what their pins were, just because I had those ones, even though it wouldn't be a particular targeted. Is that vulnerability in the original system, or am I mistaking something?
Yeah, okay, so you're concerned about the attack where you compromise some of these devices and then you can just recover some users' data, even if you aren't targeting a particular user. Yeah, so this vulnerability, okay, so to answer your last question first, so this vulnerability is present in the prior systems, and that if you compromise any one of the devices that are having some replica of the state, you can recover essentially all of the user's backups. And now, to come to your question, is this a vulnerability in our system? We show that for some parameter settings. So essentially, if you have enough of these devices, and you configure the number of devices an attacker can break into, and the number of devices that you're backing up to, you can actually make this probability quite small, that if you're randomly breaking into these devices, you'll be able to recover any user's data. And we have the security analysis in the appendix of the paper if you're curious for the details. OK, so I'll zoom back out here. So I talked about how we can define a new model in safety pin where we can have the benefits of secure hardware devices without having to completely trust them. And we can do this by tailoring the cryptographic tools to these limited embedded devices that have limited compute, communication, and storage constraints. And so in this talk, I focused primarily on my work on protecting user credentials, but I want to briefly mention my work on protecting user queries. So I've thought about how we can privately query large amounts of public data in TIPTO, which is essentially a private web search engine that allows clients to search over hundreds of millions of web pages in seconds using a co-design of cryptographic tools and machine learning techniques like embeddings and clustering. And I've also thought about how to allow users to privately query private data in Dory, Snoopy, and Waldo. So Dory is a private keyword search system. Snoopy is an oblivious key value store that scales like a plain text key value store. And Waldo runs time series analytics queries on encrypted data. And all of these achieve good concrete efficiency while providing strong privacy guarantees. OK, so now I want to zoom out and talk a bit about future work. So today, there are increasing opportunities for security failures. So users interact with a massive number of web services today, storing lots of sensitive information. And if you think about it, you probably can't even remember all the different services that you have an account at. And if an attacker finds a vulnerability in any one of these services, this can be potentially catastrophic for users. And at the same time, users have to do a lot of work in order to manage their relationships with different services. So for example, users have to manage their passwords, theoretically read terms and conditions, update their cookie preferences, set their iPhone privacy settings, update their Chrome privacy settings. And all of these things create a lot of work for users. And even if users get this right 99% of the time, if they mess up just once, if they click just one phishing link, this can be potentially catastrophic for users' security and privacy. So the attack surface today is huge, and there are an increasing number of services, an increasing number of opportunities for user mistakes. So moving forward, I want to build towards a future where instead of security failures having catastrophic consequences, we can build systems that automatically protect user security and privacy, even when there's some new vulnerability or a user makes some mistake. So this talk is one step in this direction, and I want to talk about two more concrete directions for future work. So the first is around private personalized services. So I've done some work in my thesis around protecting user queries. And today, personalized services are both a privacy risk and have limited context. So when we want to receive the results of some personalized query or some recommendations, these services rely on storing massive amounts of user data. And it's annoying for users to have to think about which services have access to which pieces of data. And now if an attacker breaks into one of these services, they have access to lots of user data. But this also means that these services now have a limited view of what a user is interested in, because the user's data is siloed across these different applications. So how can we have both strong privacy guarantees and take advantage of all of the user's data? So I'm interested in building personalized services that can provide strong privacy while actually leveraging more context. And the key idea is to put the user back in control of their data. So instead of the data living in plain text across many of these services, we put the user back in control. And so now we need new protocols that allow services to compute aggregate information across many users privately. And we need to also allow users to privately fetch results from these services. So now services only need to store aggregate information and potentially ciphertexts or secret shares of information, so the control of the data remains at the client. I'm also interested in thinking about this problem of post-compromise account protection. So today, there's not a systematic way to protect against irreversible actions after compromise. So users today have many accounts. It's only a matter of time until an attacker breaks into one of these accounts and does take some. And when this happens, we don't want the attacker to be able to take some irreversible action, like for example, transferring $5,000 out of my Venmo account. But this could also be reading some sensitive information, like my social security number, or posting something online. So I'd like to think about how we can enforce cross-account policies while preserving security and privacy. So imagine we have some policy engine that's going to seamlessly integrate with many users' accounts. And this policy engine could enforce policies that are either chosen by users or reasonable defaults. And so they could enforce things like no transfers over $1,000 per day without notifying all devices and waiting 1 hour. And the challenge here is allowing the policy engine to enforce these types of policies while still providing strong security and privacy. So the policy engine shouldn't be learning information about a user's private web activity. For example, it should be able to enforce this policy on my Venmo account, but without actually seeing all of my Venmo activity and learning lots of private information. OK, so in the beginning of this talk, I showed you how in today's systems, compromising just one component can have catastrophic effects for security and privacy. And we should instead be designing systems that tolerate software vulnerabilities, hardware attacks, and user mistakes. And there are 3 principles that I use for thinking about how we should be designing systems that can protect user security and privacy. The first is that compromise happens everywhere. So we should be designing systems with the expectation that systems will be vulnerable and users will make mistakes. The second is that security should be effortless. So we should be designing systems that automatically provide strong security and privacy without users even having to think about it. And finally, I want to try to convince you that privacy actually has the potential to enable new functionality. We often think of privacy and functionality as being at odds. Privacy is something that gets in the way of functionality. But privacy actually has the potential to unlock new data, so data across different users or even across different services. And when we can leverage more data, we can hope to enable new applications, new uses of this data. And so I've shown you some work in this general direction. But there's substantially more that needs to be done in order to protect users' security and privacy. And I'm excited to take this on. So thank you so much.
Great. Well, thank you very much. We have time for some questions.
Thanks. First of all, thanks for the talk. Very nice talk. So I had a bit of a technical question about Larch. So I was trying to understand how your design choices and constraints are tied together with the design choices, for example, in FIDO. So like, for example, if they used Schnorr signatures instead of ECDSA, which probably they should at this point, will Larch become much easier just because we have much better threshold signatures?
Yes. Okay, this is a great question. So yeah, so will Larch become easier if we can make changes to the FIDO2 spec? Definitely. There's some proposals that we have in the paper for how you could have the new version of FIDO2 that could enable Larch to become much more efficient. And for example, if you use Schnorr-based signatures, this would become much easier to threshold between 2 parties. And so you wouldn't have to do this pre-computation and have this additional storage at the log server. And actually, there is a push to have more support for Schnorr-based protocols in the spec. It's not currently required yet, but hopefully we move towards that world in the future, which would make it easier to deploy these types of systems.
And can it get harder? Like, so for example, one thing I was thinking is if you, instead of using a challenge response protocol, you use a proof of knowledge of the secret key, whether that makes your zero knowledge part harder instead? Or
yeah, that's a good point. So it's definitely possible that these updates to these protocols could actually make Larch harder. But hopefully, if these types of systems become more popular, if we can see some adoption, then this could actually influence protocols to be more amenable to Larch as opposed to becoming less amenable.
Thanks.
Another question? For me, I was really inspired by the idea of policies that could span across sites. And I was curious if you could talk a little bit more about your vision there. Perhaps, I guess one question I had was whether it would build on the concept of single sign-on and somehow broaden from there, or if you had other directions you were thinking.
Yeah, I think single sign-on could definitely be an interesting place to bootstrap this. And there's a question of how you can minimize the amount of work that developers need to do while being able to enforce these more fine-grained policies. And so I think it's interesting to think about not just policies that are chosen by individual users, but potentially even enabling anomaly detection, potentially across different users, to catch attacks as they're taking place. So how can you take advantage of this more bird's eye view of everything that's happening across the user's accounts, but without having to trust the server that's doing this enforcement with your private information?
Thank you.
Yeah.
Yes, thank you.
Yeah, thank you. Super interesting work. So I have one question. So a lot of this is, we consider that there's a malicious user that's trying to kind of steal our secrets so they can hack into our accounts and do transfers. But what if I'm just like a agent of chaos, and what I would like to do is kind of hack into some of those servers and only prevent people now from logging into their accounts? Could we use some of those techniques to try to prevent that as well?
Yeah, OK, so if I understand correctly, you're concerned about an attack where someone breaks into a server like Larch and then tries to deny availability for users. Yeah, so to address that problem, you could imagine having multiple log servers managed by different organizations and essentially splitting secrets across multiple log servers that now, if some of them go down, you can still have this logging with good availability. But this would require a different extension, and you are, in the model that I presented in the talk today, trusting the server with availability. So if it goes down, you can't access any of your accounts. Yeah.
Thank you.
Great. Well, with that, yeah, thank you very much. Thank you.